Hello, can you see my screen now? Yes.
Yes.
Okay. Should I start or do we give a break or will I just start? Okay.
Just let me a few seconds. So thank you to present this work that will be more related to robotics, if I understood correctly.
Yes,
so the floor is yours. Thanks for presenting this paper.
Okay. My present will be more like slides instead of drawings. I didn't have time to prepare, but it will be hopefully nice. So first of all, maybe there are some people that who don't know me. I will just introduce myself. Tess, and I work at Montefiore since August. Today will be a topic about the simulation to real with the help of the simulation to simulation transform with the help of the adaptation networks. And I will explain what that long title means in a second. And let us start the slides. And I'm also working with the deep reinforcement learning and at the Montefiore. So if you want to talk about that stuff, you can also come to the room and we can also talk. And I also do some podcast about the reinforcement learning. So if you're interested in that, you can also check out the YouTube. And today's paper is actually interesting result of the a lot of research that is done before that. So it's basically collaboration with the 4 companies together had a project in the 2015, and this was like a 5-year project that was able to solve the grasping problem. They managed a team with the Google AI and DeepMind and Berkeley. There's like from the different countries and different part of the United States also. They had brought a team. So all of this work today I'm gonna actually reference is the result of mostly the same team and the same work that they collaborated. And this is a conference paper also. If you are interested in the video slides of this paper, you can also check this reference. Actually, let's talk about what the paper itself is all about. It's actually trying to solve the long-coming problem with the robotic grasping and manipulation, and it tries the reinforcement learning approach with the problem. Beside this, there is a genealogy of the grasping research by the Google, and it starts with 2016, the work with the Sergey Levin's like the grasping paper, and that paper is these are all the minds that brought us here to this paper. So there's another one is called like RCAN, and there's one beside that is QTOpt, and now we have like RCAN, which is today what I'm going to talk about. And there's actually more in the 2010 and 2020 that are actually improved on this paper also. Our paper is a basically like structured as like a deep learning paper. So I will have to talk about the training phase and test phase and the results basically. And what's the problem here? The problem is in order to manipulate in the there are some options since the rise of the deep learning. People are collecting data and real-world data, of course, and this is actually a really costly process. So in order to collect the real data, you have to either label them like a normal image, or you have to use the supervised, self-supervised techniques. Like in the QTOpt, they used some kind of techniques like that. They actually use the basic sensors to module the height and able to label automatically. This is still a very costly process, and if you don't have this system, it's much more hard. So you have to basically label all of the pictures, and there's a lot of issues with collecting data from the robots. The robots are usually fails at higher rates, and it's really you need a lot of people to operate these robots, and it's really costly. And if you want to do actually even the reinforcement learning, this is more even terrible, because you have to also do the episodic manner and you have to reset the robots, and there's a lot of manual work that is actually needed. And only companies that can do such things are like big corporations. And if you are like a normal researcher with a university or something, it's really not possible or feasible to do such kind of work. So in order to overcome this problem, they actually try to find a lot of solutions, and the only logical solution is actually to able to transform policies in the real world. So in order to do this, when they tried first, of course, it wouldn't work because the domain shift with the random, because of the real world and their simulation is very big, and if you just try a policy that is learned in the simulation to the real world, it will fail spectacularly. So in order to overcome this, they come up with a lot of techniques in the deep learning history. There is one technique called the domain randomization, and one is called the domain adaptation, which is actually kind of basis for our paper today. I will just talk about what they are in the detail in a few slides. But because of these issues with the real world adaptation, it's not like straightforward to adapt the policies into the real world. Yes, it's really easy to train robotic grasping in the simulation because you have multiple computer clusters and you have unlimited computational power basically, because compared to the real world collection, it's just easy. For this work, basically overview, the main idea is that we have a simulation that is like called canonical simulation. This is the grant truth labels, and we are actually teaching a generator to learn the simulation images from these randomized images. Randomized images are basically the same images with the simulation, but a lot of the parameters are randomized to make it not look like actually the canonical simulation. You can change the textures, and you change a lot of the grasping, lighting conditions, and some part of the robot and camera. So we will hopefully learn a canonical generator function that will translate these random pictures to the simulation. In the real world, when we have a real image, since we learned the generator function, it will hopefully change this to the canonical simulation, and we can just apply our policy that is already learned in the simulation and feedback to the motors to act in the real world. This is basically the main idea of this paper. And we are using image conditions generated serial networks there. And for the policy, we are using the QT-opt, which is a state-of-the-art algorithm based works with of policy algorithms that you don't collect the data during your training, but you have a data set that is collected before. This is very crucial because in the real world of the robotics, it's very costly to do on policy training. So these are the things this paper improved actually. And during the test simulation, I will just first talk about the results, and I will just then go to the details. This paper actually works with the 70% success rate without any additional robot training. So if you have a simulation you can build up on your computer, it will be actually grasping 7 times from the 10 times you tried, it will grasp. It's really actually very impressive work in the robotic grasping. And if you do some little robotic adaptation learning, it will be even go higher as 95 or 94%. And the this is actually super impressive because the last work we had with this was the QT-opt, and the QT-opt had 600K data for the real world data for the real world graphing, and we are actually reduced this 99%. So you just need to have 1% of the real world data if you want this really good result. And if you don't want, you can still have a 70% without any real world data. That is really good. And what is the historic work of this and history of this work? This is actually, like I said, a combination of the papers. This is actually why I will explain a little bit about each of these papers in a detail, because I think they are very useful to understand how they come to this last work. First work they had was in the 2016 was the Levin's paper on the using a deep neural network to actually grasp objects with a supervised learning approach. And all of these works actually using the RGB cameras, no depth cameras involved in any of them. And they collected 1 million data with labeling, and they were able to go to the high 70% success rate. But this is what I said is a really costly process They had like a really big setup with collecting robots, and they had 3 months of the work of the real world robot data they collected. So this is, as you can see, it's not feasible. They had like 20 robots, and this is not feasible for any company to achieve such success, because even we can still train these systems, they're not very adaptable to the other robots yet, or other situations. So if you want to have like another types of the manipulation, such as you can say pushing or manipulating other ways, you have to train a system from the policy to start. So your grasping policy won't work with the pushing yet. And after that, they also introduced another paper called the RCAN. This is still used the supervised approach to calculate and control the policy. And this was actually a different approach they took actually here, because they didn't want to do with the labeling. They actually wanted to just use without labels, and they wanted to actually transform these real world images with a GAN to simulated images and try grasping positions there. This was actually not very successful compared to the last paper, but with the reduction of the labeling task that is really hard to do, it's still really good improvement, and it took clear ideas for future. And later that year, that actually introduced a framework called the QT-opt. Now with the QT-opt, they changed with supervised learning approach to the reinforcement learning. So instead of just trying to grasp from the images, they actually calculated a lot of Q-learning approaches with the double Q-learning and Bellman expectations to actually how to control the policy. This was a 96 success rate. This is like the highest. It took a lot of reward and awards for this approach, and this still actually used the real world data. So there is a still issue, as you can see. Yes, the data is actually, if you notice, the data is getting a lot of smaller, but you still require a lot of data. And with the RCAN, or randomized canonical networks, now we are at a little fewer success rate, I would say, but still the required data is much smaller now, so it's actually feasible to do in the real world, or you can even do without any simulation real world data with just simulation. This is still a really good success rate. Bear in mind it's 70%, but for the task we are trying to do, 70% could be useful. And this is basically what they meant. And besides this, there was also another work with the depth networks. I will just move about the architecture of this work. And what they had actually first with the first paper, they actually tried just to control the images with the motor. They tried to basically control the images with the controller with the images. So they collected 10 episodes, like 10 time steps of the robot, and they collected to the big data set, and they had a basic convolutional like layers, and this is not, they didn't much introduce anything besides here. You can just say, oh, I didn't notice, but it seems like the presentation is kind of frozen, no? Maybe I will just ask this, but okay. Can you hear me now? About this paper that you couldn't see now. what's the historical analysis of this work actually. And as you can see, these are the results that I actually talk in the audio. I think audio was okay with the frozen, so I will just go now. And with the Levin's grasping work, they actually collected 10 episodes. This is a really quality process, as I mentioned, and the only thing that may be worth mentioning here could be they introduced motor commands also as an input to the convolutional layers to predict the grasping success probability. But this is, as you probably notice, is not a good idea to actually do end-to-end learning with these very big data sets, because it's really highly specific manipulation tasks, so it's not much useful to do something like this. Maybe instead going with control policies or reinforcement learning approach is much better, as they already saw with their work. And this was the basic setup they had with the physical robot. And this is basically the robot they had. And the other work they had was the grasping GAN. And this was actually basically trying to create realistic images from the simulation images. So this was still using the real world data, yes, but this was only using the real world data without labeling. So this approach of the architecture they basically trained the generator and the discriminator to basic GAN structure to deal with the real fake situation. And this is still used the same kind of the grasping network they used with the first work I showed. And this was also very useful, but as I said, though, because of the issues with the GANs, as you can imagine, the success rate was much low than the other work. This was the 60%, other was 80s and 90s. And this was the realistic images they actually produced with the synthetic images, and these are the real images for the comparison sakes. As you can see, there are some clear details that might be missing with the GAN images they actually produced. I'm just gonna go to the last paper, so we will talk about our paper today. And QT-opt is another paper they actually, because of the as you can see, policy adaptations and the reinforcement learning, they had to learn a Q function, and they introduced a bunch of new features such as the cross entropy loss, and using the clipped double Q learning for the policy optimization. And here there's an actually important part which is called the cross entropy method. They use this as a simple derivative free update mechanism for getting sampling the data. So basically like a Gaussian distribution, you choose from the 64 samples and you choose the 6 samples inside of that, and you do your mean and fitting of these 6 samples, and you basically take another 64 and compute until your batch is complete. And doing that, they actually introduce a new way of the collection of the data, which is inspired by the distributed learning. And with the data numbers, they have they are still above the 500,000 data, real world data. And they also had own policy training with 10-minute rollouts. So this is actually using offline data and online data to actually get such high success rates. This was the real world setup. They were collecting real world data. The only really improvement here is actually able to, as you can see, there's some sensors here that are collecting the labels automatically without human intervention. So, but these robots still require a lot of modification if they fail, or if they froze, or if they broke, or something. And sorry, is there any messages here? Oh, yes, you can ask a question if you want to. No problem. Okay, and I will just take it later, of course. And only two things that remain for the last of the paper is that domain randomization and domain adaptation. These are really interesting concepts, but they have one negative, which is making all of this work is actually kind of problematic, which is they make the tasks unnecessarily difficult. So you want to collect a grasping object, you want to grasp an object, but why for domain randomization you basically introduce a lot of things that are not present in the original image, maybe randomized textures, randomized lighting conditions, parameters of the procedural generation. You can change the shape of the robots, you can change the physics engine, you can change the frictions of the environment, and a lot of stuff. And as you can see there, this is actually making tasks to learn something you want to learn in an ideal condition. So you are not learning in these conditions. These textures might not be even in the real life. So why are you trying like this? It's unnecessarily difficult. And in order to come these issues, they introduced a new way of the learning, which is called the sim to real by simulation to simulation. This is actually combining all of the works that I mentioned, QT-opt, the cross-entropy method, the similar network architecture as RCAN, and the other tricks they introduced for robotic collection. And to overcome the weakness of the domain randomization, they actually separated solution to the two parts. One part is the grasping module, one part is the vision module. So unlike the other work, which they had two parts of the work together, they actually separated all of this. So the policy which acts with the real robot and or the any robot in the simulation doesn't interfere with the simulation or the GAN process. So you have a QT-opt, which is basically standard now for the offline data sets with the reinforcement learning. And it's basically, they didn't even touch anything about this. They are just used as it is. And for the vision model, they used a similar architecture as the GraphCAN. So you have a you have like an image which is you randomize, and you are learning a generator and discriminator of the GAN to overcome and create simulation images. So your idea is basically you want to create simulation images from the randomized simulation images with the noisy simulation images. The architecture is basic UNet architecture, and if you are familiar with the GANs, this is probably gonna come really familiar to you. And they randomized a lot of the features of the input to make the simulation image as it was like a different image. They changed the textures the 5,000 times, and they changed the lighting position, orientation, color, position of the arm, and etc. And the output was actually they were able to produce the generatively produced image, the segmentation mask and the depth mask, and those were the features they used to train the QT-opt. So the actually police algorithm that only used this and didn't have idea if they were fake or not, or didn't care. They just used these pictures as input, and they just trained how to learn the robotic grasping with these pictures alone. So we're just gonna skip over this. I think might be time was issue, but I am just probably gonna share the slides with you you can check later. But basically you have like a four type of the loss. You have like for the segmentation and depth, you are using like a L2 loss. This is between the difference between the pixels for realistic image and simulation image. For the images you created, you are using a mean pair error, and for the GAN you are using an adversarial loss to prevent the image blurring. And this is really standard. I think the only difference here is actually this equation to calculate all of these together in one big loss function for the GANs. And these are the results. Actually, this is very interesting. As you can see, these are the first row is the source images that are inputted. As you can see, there are a lot of randomized textures. You have a lot of textures you wouldn't see in the real world trays or real world robotics. And the second row is the generated images from the GAN, and generator, and the rest is also the same images but with the mask of them and the depth images of them. So these are the results of the algorithm. So what actually this means, and what this actually means is really one thing that is important here. When you are able to create any real-world images into the simulation image, you can basically, because you can train your policy in the simulation for any interesting task like a robotic hand grasping or manipulation or solving a Rubik cube. You can do all of this with the simulation easily, but if you have also a generator that translates your real-world images to the simulation, you can basically do anything, because as in the simulation you can train anything, and in the real world you just take this and change the translation to simulation and turn it back for the motor feedback. So it's a concrete solution for this. And if you have questions, I can also take, and I think that's mostly my presentation. Can you hear me? Hello?
Yes, I can hear you.
I thought I was.
Connecting problems, I don't know. But I suppose that there is no question, then we can just stop here.
Yeah, because maybe Antoine is talking, but I couldn't hear him. Maybe I will just write it. Okay.
Can you hear me now?
Yes, yes.
Okay, so yeah, thanks, Vanand. But I was saying that I had some connection issues. So if no one has questions, I think we can thank both presenters for the very nice presentation, and see you next week with hopefully less connection issue from my side.
No problem. See you.
Thank you. Bye.
Bye.